Okay, in this podcast we're going to take a look at determining the pH of 3 different bases. All have the same molarity, but they're different types, and we'll take a look at what we do differently for each of those. So be careful, whenever you're told to find the pH of something, the first thing you have to determine is whether or not you're given an acid or a base. So obviously we have a base here because it's got the hydroxide. And then we have to determine whether it's strong or weak. So potassium hydroxide is strong. So when we have a strong base, we know that it's going to completely ionize, which means that if I start with 0.25 molar of this, I'm going to end up with 0.25 molar of the hydroxide, right? So all I need to do to get the pOH is say the negative of the log of the OH minus, which is going to be the negative of the log of 0.250 molar, and that's going to give me a pOH of 0.602. So my pH is simply going to be 14 minus the pOH, which is 602, so that's going to be 13.398. And that number makes sense. First of all, there's 3 sig figs in my concentration, so there's going to be 3 in my mantissa with my pH. This number makes sense because I have a strong base, so the pH is going to be very, very high, close to 14. Okay. So here we have barium hydroxide, same concentration. So it is a base, and it is a strong base. But the thing that's different here is I have 2 hydroxides. So what happens if I have barium hydroxide and it ionizes, which it will completely in water, right? That's the definition of a base. For every one of these, 0.25 molar of this, I'm going to end up with twice as much of this, right? Because I get 2 hydroxides. So now when I do my pOH, I have to say is the negative of the log of the 0.500 molar, which is going to be 0.301. So my pH is going to be 14 minus my pOH, which is 0.301. So that's going to be 13.698. And that makes sense. Again, very high pH, even higher than it was with potassium hydroxide, because for every 1 molar of the base, I get twice as many hydroxide. Alright, so strongs are easy. Weaks just take some work, right? So here I'm given ammonia. I have to recognize that that's a base, and it's a weak base, and it's giving me a Kb, which is pretty small. So the first thing I have to think about is where do the hydroxides come from? So if I take my ammonia and I put it in water, what's going to happen is I'm going to end up with ammonium ion and hydroxide. And it won't completely ionize, it's a 2-headed arrow, so if I start with 0.250 molar of this, and I start with none of these, this is going to lose X, this will gain X, this will gain X. So my ice table, my equilibrium is going to be 0.250 minus X, X, and X. So what I know is my Kb, which in this case is 1.8 times 10 to the minus 5, is equal to my products, which would be X squared, over my reactant, which is 0.250 minus X. Now, because my Kb is so small, I know that my X is going to be tiny, so I'm going to use my simplifying assumption and get rid of that. So if I cross multiply 1.8 times 10 to the minus 5 times 0.25, I'm going to end up with, let me see, 4.5 times 10 to the minus 6 is equal to X squared. If I take the square root of both sides, I'm going to end up with X equals 0.00212. And that's my hydroxide concentration, right? So my pOH is going to be the negative of the log of 0.00212, and that will be 2.673. So my pH is going to be 14 minus 2.673, or 11.32. I want 2 sig figs in my mantissa. Actually, I should have 3. So I'm not sure what that third one is because I did this before I don't have my calculator now. Okay, so we're going to stop it right there. And it makes sense that this number's smaller, right? Okay.